Professor Ghosh has written 13 books and the textbooks by him are widely followed in India and abroad. Currently, he is an emeritus scientist of the Indian National Science Academy, New Delhi. Professor Ghosh is fellow of all the 4 science and engineering academies of India. I request Professor Ghosh to start his keynote speech. This session is going to be chaired by Emeritus Professor Shiv Gopal Kapoor, University of Illinois, USA. Thank you. Caller mic, please.
Hello, can you hear me? Okay, so very good afternoon, dear friends, and to start with this presentation, I don't call it a keynote speech, frankly speaking. So I think before I make my short presentation, I would like to confess something, and that I would like to start with a story about one student who was appearing in a science examination. What happened, you know, that he in the question for writing an essay. So he wrote that 3, 4, 5 pages with a lot of enthusiasm, and he wrote on iron. Then, you know, towards the end of the examination, he went to the washroom, and there, you know, sometimes what happens, the students, they whisper amongst themselves. So his close friend was in another hall. So he was also there. He said, "Hey, how did you write that?" He said, "Yes, Lord, only thing I could remember, the origin of the name of that ore, you know, iron ore." Then his friend said, "Why you did that?" He said, "No, this iron I am writing." No, the question was not an iron, it was an ion. He said, "Oh my God." So he hurriedly came back. Hardly 5 minutes was left. So he was very innovative. So he tried to take up the situation under control and remove all the R's wherever he wrote out. So his essay, he thought, was on ion. So I also originally, when I was asked by Professor Chattopadhyay to be present here to give a talk, I assumed that it will be on manufacturing, and so I prepared that. That is the subject I know a little bit. But just 2 days back, I think Professor Roy sent me the brochure. I found that the conference is on translational research in metals and materials. Again, I followed that student and tried to cross all the R's in my presentation. So what you will see is a result of that. So, and if you think it is something hilarious, I'll be happy. And if you think it is a wastage of time, then the fault is completely mine. Thank you. So I think what I try to do, as I mentioned, I wanted to cross the R's. So we see that this term translational research is of somewhat recent origin, and it is used primarily for the research in the area of medical and biomedical area. Most of the time, translational research, this term has been used for the research in these areas, which implied that the results could be directly from the lab to the patients. In case of medical science, you know, the formalities are much more in taking something from the lab to the patient. And so therefore this was something, very new idea, and that's where the philosophy of translational research started. And then applying this to engineering is very recent, as has been mentioned during the inaugural session. And it is hoped that translational research approach can help innovation and a fast progress of economy. Since many of the concepts are still not mature, the topic is somewhat nebulous, I must say. I myself do not understand all except translational research, but an attempt is being now made to understand its link with what is called engineering science. Because innovation and invariable requirement for that is engineering science, which unfortunately I notice is being gradually ignored in our curricula. So, it should be remembered that the involvement of scientific principles is often not through its raw form, but via a middleman called engineering science. Like, we don't discuss about atom-to-atom interaction. We go, if it is a solid one, we go to solid mechanics. If it is not solid, binding energy is less, then we go to fluid mechanics and so on. So the importance of engineering science should be properly recognized, and how it helps the progress and innovation needs to be formally recognized. And this recognition helps in framing various curricula and training programs that can lead to major innovations in manufacturing that may usher the world into the realms of the next industrial revolution. Now, to understand the presented material better, first a quick look at the fundamental characteristics of science and engineering is taken. You see, it is being misused most often, and most of the cases I find people don't understand the fundamental difference between what is science, what is engineering, and what is technology. Quite often they are mixed up. So I think it is better at this stage to have a clear understanding that what are these and what is the relationship amongst them. So you see, science, this word science originates from the Latin word scientia, meaning knowledge, knowing, creation of new knowledge, like that. I can give one example. Say a phenomena which is called spontaneous and stimulated emission of radiation. You are all familiar with that, that when an electron is at, I can sit, okay? You permit me to sit and give the talk. Thank you. So we can, sorry. So you can see that when an atom is at a higher energy level, an electron goes to a lower orbit, emitting some radiation, a photon is emitted. On the other hand, what can happen that an atom is at a higher level, an electron is at a higher energy level, and a photon passes through which has the exactly same energy, which is the gap between the two levels, then another photon radiates, which is exactly in coherence with the previous one. That's where they're exactly same in frequency, etc., both in phase and time. So this is called stimulated emission. This is something which the physicists have discovered. And now what is the use of that? So you will see that engineering is the thing which originates from the Latin word ingeniare, which means to innovate, to contrive, to devise. Such creations come directly from basic science. It is also related to Latin word ingenium, implying cleverness. Thus, when the basic science of stimulated emission is employed for practical purposes, we get laser. How we get it? You know, then it is an engineering concept to, this is not showing the, yeah, okay. So I can, you know that, this is now at a school level, that a photon is actually between two parallel mirrors, they go back and forth millions of times, and in the process they create huge number of photons which are all exactly same in phase and everything frequency. That means ultimately when it becomes too strong, it comes out through the partial mirror as a strong coherent laser beam. So this is the innovative way of utilizing stimulated emission, and that we can call as engineering. So by engineering of stimulated emission, we get a strong beam which we call laser beam. Next, once an extremely powerful coherent light beam is produced through engineering, its application to various real life work like manufacturing, communication, material processing, etc. is the activity that is called technology. So the technology word originates from the Greek word technologia, meaning systematic use of craft, art, etc. It is also related to Sanskrit word takshan, which I will not go into details. But therefore now you see technology comes last. It is whatever you have produced or evolved or innovated through engineering, its practical use for various kinds of useful one. That becomes technology. So there are three distinct things, which you have to keep in mind. That is like a laser beam is being used for cutting or drilling, and there are so many things. Now, so the basic characters of science and engineering, therefore, we can say that in science, the basic feature is analysis using the scientist, whereas in engineering, the basic feature is characterized by synthesis, that is putting things together, and that is done using the capability to innovate. Science, what is the output? It is the new knowledge and better understanding, and in engineering, the outputs are products, both physical and non-physical. This is the usual thing. People think engineering is below, science is ivory tower kind of thing. Now, engineering science, where is the engineering science in this whole scheme described just now? It can be explained as follows. Now, basic science in its raw form, it is the discoveries made in the laboratories or in the minds of the scientists. Then science in its usable manifestation, I will give some examples later. This is engineering science, and engineering science can lead to engineering and technology in most cases. There are cases where you can directly translate the science innovation to engineering, as you have shown, but most of the time you will find that means when you design something, you use solid mechanics, fluid mechanics, thermodynamics, heat transfer, all kinds of things. These are not basic science, but they are directly related to science. So they are something in between science and engineering, and that's why those kinds of subjects are called engineering science, which are directly giving rise to all kinds of engineering activities. Now, so one or two concrete examples can be made that idea of this engineering science. So consider a very large number of atoms interacting very strongly with one another. The overall result is some relations between the external forces, the control volumes, deformation, and failure. And this subject providing the gross characteristic is called solid mechanics. That is an example of engineering science. Similarly, consider a very large number of atoms interacting weakly with one another. The overall result is some relations between the external forces called pressure, the control volumes, deformation, and displacement, and the subject providing the gross characteristics is called fluid mechanics. These are the examples of engineering science. Now the following slide shows some examples of applications. All these can be possible only when a strong understanding of the relevant engineering science exists. And you will see that modern engineering is going in a direction where a better understanding of engineering science and a much firmer grip on those will be essential. Otherwise, you can do only imitating something existing, cannot innovate, cannot create most of the new things. Say, for example, if you do nowadays, it is possible because we have large capability to make large computational programs. Say, molecular dynamic study has become very common. Through that, if you start, you can develop many of the things which we otherwise earlier couldn't do. And we could only make something, do experiment, and then you get the result. But now, through computational simulation, you can do many of the things which you can get. Similarly, the crystallized solids, these are the defects, or the dislocations. And this dislocation dynamics modeling can study that what will be ultimate situation which leads to work hardening, etc., theoretically, without doing the experiment. So this is another multi-scale computational mechanics you can do starting from the atom level, and gradually you can go up to almost mesoscopic level, and you can understand crystal plasticity, behavior, etc. The basic advantage is that many things you don't have to really make and prepare that alloy or that material with that composition and do the experiment. You can think of it and you can make a theoretical model, do the computational modeling, and get everything, including the microstructure, strength, all the kinds of characteristics. Say, for example, again, how engineering science helps in innovating things. I will give two examples in manufacturing. So, understanding the fracture mechanics of hard and brittle materials and that of tough and ductile materials led to the development of ultrasonic machining using the application of vibration theory. Say, you know that this is a tool which vibrates at very high frequency. Tool is made of a tough material and ductile, and this workpiece is a brittle material like a grass or something, and you have the abrasives. But you know, because of this, that this will get fractured and eroded faster than the tool which is made of ductile. So this kind of difference of materials could help you creating a situation where you can use it as a manufacturing operation. Similarly, a better understanding of the selective anodic dissolution led to the development of electrochemical machining. And also, later, a much better understanding of gas evolution and bubble formation due to electrolysis process developed the new hybrid process called electrochemical discharge machining. All these things were possible through a better understanding of the science involved, which we call not pure science, but engineering science. So this is also a machine learning program for simulating the microstructure. It is theoretically possible. I saw in Japan and also in Ohio that they had long back, theoretical, they call virtual alloy project. You theoretically describe the basic elements, composition, etc., and then theoretically predict the characteristics and also the microstructure. So, like governing equation of fluid mechanics, which you use finally in Navier-Stokes. But when it comes from, you can start from microscopic scale, then this lattice Boltzmann modeling you can do, and you can ultimately get the Navier-Stokes equations. And a better understanding of fluid mechanics problems can be addressed from the molecular level through mega-scale computer simulation. But the convenient way is to use the Navier-Stokes equation. So we don't start here. We use the result directly from the engineering science part of it, not the basic science part of it. So again, you know that a good understanding of fluid mechanics can help to innovate very useful applications in the biomedical field using the knowledge of fluid mechanics at micro levels, which they call these days microfluidics. It has very special characteristics and it has very special applications in many areas which are being used now for developing devices, etc., for medical diagnostics and so on in the healthcare sector. This is also, in polymer science and material science, the molecular dynamics simulation, it can determine the thermophysical properties of polymers also. So you can see it is molecular dynamics of a particular situation which you do. Then directly you can get the theoretical characteristics you can show by the red lines, and if you can make it and do the experiment, you get these experimental results. So therefore, this is very useful when you are designing or innovating something new. You don't have to make everything and to experiment and use the trial and error method. You can directly compute, and using the principles of engineering science, you can get the result. And then with various choices, you can get something which can be something very useful. So innovation becomes very easy, and rather I will say, rather I'm not possible, but I think can be accelerated through the use of proper use of engineering science topics. Like say for example, if you understand how to make a surface hydrophobic and how to make a surface hydrophilic, now this interaction of molecules can help in designing hydrophobic and hydrophobic surfaces, and proper manipulation can lead to successful self-assembly of materials. That is considered as a major goal for futuristic manufacturing, where material will assemble themselves just like living objects too. It is very important also because you will know that when you discuss next the bottom-up manufacturing, that it can be practically meaningful only if it can be done in a reasonable period of time, not taking hundreds of years. So, and that is possible only through self-assembly of material. So, I will show you some examples. So, how do you do self-assembly? Say you have a piece of material, basic element, where these surfaces are, say, hydrophobic. That means it will try to avoid contact with water. If you make more such particles come in contact together, so they will be attracted by some fluid, like say your capillary action, but then it will try to keep the area exposed to water minimum. So what happens? If they are connected very strongly, it will not happen, it will remain like that, and you will get an amorphous structure. But when the contact force is less, then what will happen? To minimize the surface area exposed to the water surrounding it, it will become like this automatically. You don't have to do anything. So again, another particle comes, it goes, it becomes like this. So this way, a very ordered, definite shape can be generated using self-assembly. So this is possible. I can give you some. Suppose you have a molecule, one end as a hydrophilic functional group. This is done very much in medical science by drug discovery and so on. And another end is hydrophobic carbon chain. So if you have to orient them in a particular way, so that all the functional ends in one, and suppose some billions of such molecules are there, you cannot do it one by one. So best thing will be to do it by themselves. So put them in water, automatically all the hydrophobic functional groups will be below, and the hydrophobic carbon chains will be avoiding water. But with different concentrations, you can have a bilayer, where again all the hydrophobic ends are trying to hide among themselves the contact with water, and it can be also mishals also, that where all the hydrophobic ends are inside. So this is all done automatically using different kinds of concentration. Similarly, suppose if you have a hexagonal element, alternate sides are hydrophobic, alternate sides are hydrophilic. If you put more such thing, what will happen? All the hydrophobic ends will try to come together so that they are not in contact with water. So with more and more elements coming, you will get gradually something produced of this form. But if all the sides are hydrophobic, then they will try to come together in this manner, so you will get this kind of a shape. So it is a very primitive form of self-assembly. Nature does, it is unbelievably complex process. But this is the basic idea, how you can produce a definite shape using some basic elements designed that way to give you a particular type of output. Like if the basic shape is there, these red sides are hydrophobic, so then it will keep on growing in a manner so that all the hydrophobic ends are contacting themselves so that they are not in contact with water. So this is, you can see, you can do properly if you understand how the hydrophilic surfaces can be created, and that is a part of understanding the basic, rather related engineering science. So the understanding of these manifestations for manifested form of basic science can be used by engineers for developing processes, systems, etc. So engineering innovation yielding newer technology is a key requirement for progress. For the progress of economy, such continued innovation is essential, as only innovation can result in appropriate value addition. This is something very important for us, for our Indian manufacturers to understand. We are also doing a lot of manufacturing, there is no doubt. But there is a fundamental difference, as I explained. Now, to attain economic superiority, this value addition is very important. And I will explain this with the help of a slide. So you see, we make very good cars. Our Indica car made by Tata is, they are quite popular in East European countries once. Each Indica car costs about 4 lakhs of rupees, 400,000. So suppose you are 500 cars you are exporting. So it will take 5 ships, and total amount you will earn 500 into 400,000, that is 20 crores or 2 crores, 20 million. Now, America sends you one product, say one helium ion microscope. So that will cost the same amount, 2 crore. They will send only the box, 2 meter by 2 meter by 2 meter. They don't have to send something in 5 ships. Mainly because why? The product here, the value addition has been very high. So one unit costs so much. And here, you have produced motor cars, the value addition is not that. So for example, a woodcutter goes to a forest, brings a wooden log, spending his whole day, he comes and sells it at 100 rupees. And that log is used in some sawmills, and they make it planks, etc. They sell it to some furniture company in say 1,000 rupees. So 10 times. And those furniture companies, they make furniture out of those, and they sell it at 10,000 rupees. So that is what was actually the material wise cost only 100 rupees became 10,000 rupees. So this value addition is also one point we must remember. Otherwise, just doing trade, we are not going to have any superiority or any advantage. Now, in order to address the above mentioned problem, it will be necessary to achieve many innovative transformations of the existing processes through which things are designed and manufactured. Thus, it may not be totally out of place. Now I am saying that I have crossed all the R's and say, let us try to see that if I bring some of the R's back. So, so something about manufacturing I can mention, just you are familiar with some of the things. Once manufacturing left the earlier garb of craft and became a part of engineering, its relation with science became intimate, as in the case of other branches of engineering activity. Thus, the progress of manufacturing became closely linked to the progress in science. So to chart out an optimal route to the futuristic manufacturing activity, it may be desirable to understand the concepts involved in the whole range of activities we call manufacturing. Manufacturing means one is processing and management. That actually leads to country's economy. And very important to realize that achieving excellence in manufacturing is possible only through innovation based upon the application of advanced scientific principles. Then only you will be going into the forefront and your value addition will be possible. Otherwise, you will keep on sending your raw materials, as India has been doing, sending all the excellent quality raw iron ores to Japan and buying steel at 100 times or maybe 1,000 times more price. The same, whatever Mother Earth gave us, we are getting back the same thing, paying 1,000 times more. So, the manufacturing, it is like this: materials engineering, raw material, then tools and dies, the primary processes like your casting, forming, then joining, these are the processes. And mechanical engineering also is involved. They are very closely linked subjects. It is relative motions, drives, control, material handling, machine tools. So they combine the This was the primary processes. Then secondary processes use more of mechanical engineering, as you know. So that's why this part of manufacturing has remained in the materials department or metallurgy department, and the machine tool related things have gone to mechanical, where you get the final product. The fundamental characteristics of all existing manufacturing processes can be understood by considering the following aspects: energy type, mechanics of material removal, energy source, manipulation and control. Through innovative exploitation of relevant engineering science involved, many non-traditional manufacturing processes have been developed as shown next. The energy types are mechanical, electrochemical, chemical, thermal. Mechanics of material removal can be so many. Energy source used can be so many. And then manipulation and control technology helped in automating manufacturing systems. Revolution in electronics and computer engineering has drastically changed the manufacturing scenario. But one thing now finally I will mention, the basic thing has remained changed, not changed. And that the paradigm shift has been here. You are familiar with this. This is the Kailasa temple at Ellora. You can see it's a huge structure, but cut out of one piece of stone. It's actually real wonder. You know, those who have visited, they know. And this is the human beings you can see. And the whole complex is unbelievably complex. And the whole thing was cut down from one piece. So this is one way of making things. Another way of making things is this. So you just keep on adding small bricks and ultimately you erect a huge structure. So what is the basic fundamental difference? In the other case, we call it a bottom-up, a top-down approach, which has been our case, by taking a piece of material and then give the shape by cutting out some extra material, etc., or deforming it into the proper shape. And the other thing is that here it is the bottom-up approach, where you keep on add small elements to give the shape, which nowadays people are calling additive manufacturing. So the bottom-up approach is like this. You have the CAD model, sliced it into it, and then generate it like this, so that ultimately you get the whole thing. And you know that these processes are now generally quite common. They are called additive manufacturing processes. So this is the modern trend in futuristic manufacturing, the direction in which it is going. And the following a couple of slides will symbolically indicate the progress of various engineering science areas, helping necessary innovations to achieve many exotic processes and engineering applications of the acquired knowledge. This will help in what is called translational research, that will make it feasible to integrate the research labs and the application area. That is the actual basic thing of idea of translational research, that they will be directly linked, not through a long process with a long delay. So the traditional engineering subject, what I am telling from the point of view of a teacher, how our curricula, etc. should be reformed if necessary, is this, that the traditional subjects which will continue, you have to add mathematics and large-scale computation because of extensive simulation and modeling which will be necessary. Life science will be a part of it, physics and chemistry will be part of it, and engineering, or the curricula of engineering science in the coming days will be of this, where it will be this along with the excessive or extensive use of basic sciences. So manufacturing is going like this: materials engineering, mechanical engineering, this gives to traditional manufacturing, electronics, computer engineering, modern automated manufacturing, physics, chemistry, polymer science. Then when they combine with this, gives rise to advanced manufacturing, and when principles of life sciences are also going to be integrated, we get the futuristic manufacturing. So, sorry, I don't know what is happening. So you can see what the that means what the subjects will be now necessary for you. What is the knowledge base for conventional engineering will continue. Then simulation and molecular engineering will be very important, as I have shown. Synthetic biology is coming up, which will involve self-assembly, etc. Like things will be designed artificially by engineers, but they will be following the principles of life science in many cases. Smart macromolecules and intelligent materials will be another part. Fabrication by self-assembly of materials, artificial intelligence, self-learning, self-correction, and finally self-replication. All these are going to lead to the knowledge base for new era of engineering and translational research. And the primary components of futuristic engineering are indicated next very symbolically. So what will be the futuristic engineering? One concept will be miniaturization, another will be massive parallelism, then bottom-up fabrication and self-assembly based mass manufacturing, embedded biochemical energy source and control electronics, and materials-wise, most of them will be smart materials. So, I think what I'll do, I'll end here. In future, another 30-40 years, what may happen? Many of our machines will be working using the solar energy, not through photovoltaic cell, but using an artificial photosynthesis process. Through that, what will happen? All the carbon dioxide will be consumed, and what will be produced is oxygen. So, whole of our polluted environment will be completely clean with the help of industry. So, industry will be, rather than polluting, they will be cleaning agents. That is a possibility which may happen through the use of this synthetic biology and futuristic engineering. These are the possibilities which you have to keep in mind. And so therefore, a strong understanding of the relevant engineering science is going to be the key feature which you have to keep in mind when you design the futuristic curricula. I think that will be all for your kind attention. I don't know whether I have been successful in removing the R's from my iron word and make it 11 to iron. So I thought that I am myself not a very active researcher, neither translational nor rotational, but I thought I'd tell something point of view of a teacher, that what kind of modification or attention you have to pay to our curriculum for making the next generation engineers. Thank you very much.
Thank you, Professor Ghosh, for such an enlightening speech and telling about the emphasis of engineering science for translational research. That's a key message which he is delivering to us. So, take questions for Professor Ghosh, which he want to share, some ideas. Yeah, please. Yeah.
Yes.
I'm really delighted to be here. This is one. The thing is that these things has to be told to the apex of the educational system.
You represent one of them.
Yeah, I certainly do that. But moreover, maybe IICT or those things. You know, the system what we have got. When we have made a small attempt to change here at our place, and we realize that the students cannot appear for the GATE exam.
Yeah.
I mean, that's something very important. The concepts what you are told, they're absolutely relevant for today and tomorrow. Not tomorrow, but today and tomorrow. But as a new NEP policy, new education policy, it has got a wide scope and it could be incorporated. The logic what you are given to us, it could be incorporated in that NEP policy. And with this first of Government of India, I think that the apex officers will also be in know of the things. So they will be very flexible even for the GATE, PhD, and all the competitive exams and all the structure of academics in that field.
The main thing, you know,
that is what I feel.
Professor Arjunwadkar, that there is a tendency of making all the programs identical. You have thousands of colleges and institutions.
Absolutely.
Why everybody has to follow exactly the identical program? There is no need. You can have all different shirts, different colors. Are you all in uniform? No. So I think this concept that everyone should follow a strictly prescribed kind of curriculum, I don't find much reason, because the vast country with a huge number of institutions and still more huge number of students, why everybody has to learn the same thing? I don't understand that. So there should be variation.
Appreciated, sir. Very, very much appreciated. Thank you.
Thank you. Thank you very much.
Any other comment, discussion?
Thank you, sir. I have one of the very small query about what you have told related to the microscope, particularly the helium-ion microscope. As a metallurgical engineering, I am interested in the microscope, but this is the first time I have listened from you. So would you explain about the helium-ion microscope?
Look, actually I made a mistake. The cost of a helium-ion microscope is not 2 crore, it is 20 crore. And there is only one such at IIT Mumbai. I saw it. So I think it is extremely expensive equipment. It is 20 crore. So unless you have, in my opinion, such equipment should be shared between various institutions and universities. There is absolutely impossible for one institution to make 100% use of such kinds of elephants. So if at all any such thing like a helium-ion microscope should come to eastern part of India, there should be only 1 or 2 places, not more than that. One only now exists at IIT Mandi. I have seen that. Maybe some other research institute, but in academic institutions among the IITs, only Mandi IIT has it.
So what application?
And because I think its resolution, etc., is very high. That's what I was told. I am not an expert in microscope, but they told, I saw that its resolution, magnification capability, all those things are much superior. That's all. I think Professor Vikramjit Basu can tell you better.
Thank you again to Professor Ghosh.
Thank you, sir. The next keynote speaker for TRMM-2023 International Conference is Dr. Marc Madou. Let me introduce the speaker. Before joining Tech de Monterrey, Marc Madou sir was a distinguished professor and part-time entrepreneur in residence at Autonomous Medical Incorporated Institute. He was a distinguished professor and Chancellor's Professor in Mechanical and Aerospace Engineering at University of California, Irvine, where right now he is a distinguished Professor Emeritus. Before that, he was Vice President of Advanced Technology at Nanogen in Santiago. He specializes in the application of miniaturization technology to chemical and biological problems. He is the author of several books. In this burgeoning field, he helped pioneer both in academia and in industry. He founded several micromachining companies and has been on the board of many more. Dr. Madou has more than 350 peer-reviewed journal papers and conference proceedings, more than 200 plenary and invited talks in the last 10 years, 8 books published, 25 book chapters, and 27 patents. He is considered as the pioneer of 2 research fields that are now being pursued worldwide. One is carbon micro and nanofabrication, and the other one is compact disc fluidics for molecular diagnostics. On behalf of TRMM 2023, I welcome you, sir, and now the podium is yours. Yes, sir? 91 as on October 2023. Welcome, sir.
It was nice to have Professor Ghosh give a talk that kind of summarizes so many things we've done together over the years, ending up in self-assembly. My talk today is very different though. It's very engineering oriented, very translational actually. We're going to be talking about PCR. Yes, I know that this is a group that mostly knows about metal engineering. Although my talk is very much materials oriented, it's not only metals. A lot of it is actually very clever choice of materials. I hear some kind of pinging. Thank you. Thank you. So, as you can see, the title of my presentation is Rational PCR Reactor Design. The work I will present is all very new. It comes from my current position as entrepreneur in residence at ANDI. So, because some of you might not know what PCR is, just to remind you, it's a technique where you have a very small amount of liquid with some DNA or RNA, where through heat cycling, by going several times between a lower and a higher temperature, each time you cycle, you double the amount of DNA, RNA. And as we all know, this has really caused a revolution in medicine. And during the COVID crisis, PCR really showed its metal. That's interesting. It's like iron and iron. And I will show you that despite the misery we lived through, all of us, through the COVID, technologically actually there has been a lot of innovations that occurred. And so the things I will cover is, so I will talk very briefly how the COVID crisis really acted as a point-of-care technology accelerator. What one means with point-of-care technology accelerator, well, POC is point-of-care, it means can I actually use PCR at the point of care, meaning perhaps you go to the doctor's office and you don't need to send your sample out. You can actually, during the doctor's visit, get the answer. Yes, you have COVID or not. So you don't have to wait a couple of days. I will then much more specifically dig into the goal. I think this has to do with the frequency of the there's no matched frequency of the signal, I think. We probably have to change the resolution, but I'm afraid that might take a lot of work. Do you know what I mean? It's, okay, good, that's good. So I will keep on talking in the meantime. So the goal and the test bed is RT-qPCR, so I need to explain this word. RT stands for reverse transcriptase, and what it means is several pathogens, or RNA, DNA, like COVID is an RNA virus, and you have to translate it from RNA to DNA, so that's the first step. Now, very confusing, the Q stands for real-time PCR, means you're seeing the amplification in real time, but then you would end up with RT-PCR, so most people write RT-qPCR. Then I will talk about the implementation of this RT-qPCR, and that is where engineering will come in. So we all understand the science principle, right? As Dr. Ghosh, Professor Ghosh explained, the engineering is the practical utilization of a science understanding. And the implementation will involve these 3 or 4 important parameters that we know to start with we need to do correctly, implement them correctly. The first one is the sample to answer time. What that means is, how long does it take from taking a sample, let's say saliva or nasal swab, to your result, you have COVID or not. And in this exercise, we have set as a goal 10 minutes. And that means 10 minutes all the way from extracting the RNA or DNA from your sample and amplifying it. And that's a big challenge, you can imagine, because today it often still takes 4 hours. It might take 2 or 3 days. But so this is not really a scientific thing. This is just from the market that we know. Doctor's office, in average now, is between 13 and 16 minutes. I don't know if in India it's much longer. It might actually be shorter, you know. And so if during the doctor's visit you want to know if you have the disease, you need to do it less than 13 minutes. So we have picked 10 minutes as our goal. So that will be number 1. The next parameter is called the LOD, limit of detection. Now, the best possible DNA equipment out there, very expensive, big, and it will take a long time, but it's very good. It will give you a limit of detection of 100 copies of that virus in a milliliter. So remember that word. Remember that number, 100 copies of RNA in 1 milliliter. That means if you would have a piece of equipment that can give you results in 10 minutes, and it does 500 or 1,000 copies per milliliter, actually you would be very good. That really would be a winner. Now, in that context of limit of detection, I'm introducing this Mr. Lambda. So the first here was sample to answer time in less than 10 minutes, so that's the first parameter. The second one is this Mr. Lambda, and you will slowly understand what this is about. It really means how many copies do you have per reaction chamber. You know, if I would have a reaction chamber that has 10 copies per reaction, lambda, per chamber, lambda would be 10, right? Now, why it needs to be bigger than 3, I will explain later. But so that lambda is very connected to LOD, and it's very connected to multiplexing. In biosensors, it's so key that you don't only measure one analyte. In this case, you want to look at all the possible infectious diseases. maybe influenza A, influenza B, COVID, and each of those would be a channel. And so multiplexing is this N, how many analytes. But now, for the engineers, where I hope to get to, and I hope the younger people in the audience appreciate this one, that the key that will determine all of this, succeeding or not, is the thermal efficiency gamma. And the thermal efficiency will be how fast can I heat up a certain volume of water. It sounds like a simple thing, right? But you will see, it is actually a real key parameter. And that will include the choice of your reaction chamber, the choice of your heater, the thermal contact resistance, a lot of modeling, and a lot of thinking about what materials you choose for this purpose. So that will be thermal efficiency, and then I'll make some conclusions. So I want you to focus on these 4 things, right? 10 minutes, Mr. Lambda here, and we will see that it should be larger than 3. And then gamma, which is the most important parameter, I said. You cannot understand yet why I put these numbers, but I will already give you a bit of the feel. You want to have, in the smallest amount of time, and you can see I put here 8 minutes, not 10 minutes. That's because I need to do some sample preparation. So 8 minutes of that heat cycling, and you want to do that with as much liquid as possible. So you want to make this smaller, and you want to make this bigger. This you already understand why, right? That's dictated by my request or my aim to do it in less than 10 minutes. This one, why 20 microliters, right? But you will see that is actually where the science and technology is at. If you could come up with any technology that can have a better heat efficiency, that is being better than 0.4, you have a product. That's going to be the idea. You will see that in our case, we've been able, well, I shouldn't say that. You know, in industry, people have to exaggerate actually more than in academia to get money. So, but here, I'm old enough to actually just tell the truth. So, we wanted spatially multiplex, that means 8 reactors, and spectral multiplexing 4, that means 4 colors. That's 32, that would mean our aim is that we have 32 different analytes that we can measure. So if you go and click, we can talk first about this COVID as a technology accelerator. You know, probably in India, just like in the US, the COVID-19 pandemic, it led to a relaxation of a lot of the regulation towards product approval. It also gave a tremendous acceleration in innovation, and ours is kind of a result of that. To tell the whole story, actually, since the COVID now has abated, for now, we have seen tons of companies fail, by the way, backlash, whiplash, because now suddenly they can't sell anymore, right? And that's why you just have to say, okay, what did we learn, and apply it more broadly to other things than COVID, because this is generic, the developments we're talking about. So, to illustrate that, this acceleration of innovation in bioanalytical techniques, I made this graph here, and this shows the limit of detection, that's that LOD, and you can see we go from really pretty poor, 1 micromole, to 10 to the minus 21. So you're getting at the molecular level here, right? I mean, a few molecules, not the molecular level. And this is the detection time. And if you look what happened, so PCR used to be up there 4 hours, 2 hours. And through all of that money in the COVID time, the PCR now has gone down, down, down in time, but not in cost, because often it's still too complex. So again, for people that are looking at a way to innovate, it would be to make it much simpler and also much faster. Today it's not together yet. This is really weird, you know. In 2018, 2019, if anyone would have said that PCR could be faster than lateral flow assay, you know, traditional lateral flow assay or signal amplified lateral flow assay or ELISA, they would laugh at you. They said, no way. And look what has happened. So can we take advantage of that, right? So kind of summarizing, as a result today, RT-qPCR can be as fast or even faster than ELISA and LFA. This benefits point of care genetically, way beyond COVID. So where are you today and what are the goals? It will be a little bit repetitive, but it's good to be repetitive, so if it didn't sink in the first time. So we wanted the sample to answer of COVID-19, RT-qPCR in less than 10 minutes, because that's about half the time of a doctor's office visit. Now, still not explaining why, but the sample volume actually should be as large as possible. You know, I can already give you an intuition why that is. If in your body you have, you know, in 1 milliliter of blood, only one pathogen, you should have at least 1 milliliter, right? Because you might take a milliliter and none will be in there. You might need 10 milliliters. So the more volume you have, the more chances you have to have that species in a significant amount. That's the first intuitive kind of reason why that is. I already said we want a limit of detection that's less than 500 copies per milliliter, because the best one is 100. And we want a multiplex, you know why that is, because you don't want to just do one pathogen. The more you can do with the same instrument, the better you're off, of course. And then given the setting, you want it to be portable, simple to use, inexpensive, low power, all the usual stuff. And you know, for me, this is very intriguing what I'm just saying, because over the many years I've worked with colleagues here in India, especially Sabadal Saha, Dipankar in IIT Guwahati, we actually, and this is what you guys should focus on, we want to go from point of care to extreme point of care. What that means is your power might not be there. It might be a dusty environment. And you have an economics that's totally different. The economics is you should have probably the disposable, an instrument 10 times less expensive, but you have probably 100 times bigger market because of the population. But to get there, how do you get there? That's always the problem, because typically in a capitalistic, normal working operation in the West, someone will invest the money and they want to see a quick return. You know, no one is there to help you to cross that bridge. And that is a key issue. Now, where are we kind of in terms of products out there? So the Cepheid Express has a multiplexing, and 45 minutes or less, it's on the market. Actually, the Chief Technology Officer of Cepheid is one of my former students, and that company is one of the really leading companies today in PCR. The next one is more experimental. It's not really on the market yet. It's Cryptos biotechnology. And here, the heating and cooling of the sample is done with plasmonics. And so plasmonics, again, is one of the things you should look at as a new way of heating and cooling small amounts of sample. This is work that came out from Luke Lee at UC Berkeley. Now, a product, again, that's on the market, and that's the one to beat. That's the one we use as a reference, and everyone does, but look what a company is, it's a Roche. And so they have this device. The thing he sticks in there is what comes out of your nose. He sticks that in this plastic structure, and that plastic structure holds these PCR reactors we are talking about today, which are these small volumes, will heat cycle to get your signal of the RNA, DNA that's in there. And so they can do it in 20 minutes or less. And we want to do it in 10 minutes or less. That's how the system works, right? That's the one to beat. Now, to do that, we do reverse engineering, you know. So we take that machine and we look at how do they get to 20 minutes in that operation. And you can see I have put a timeline here, and each of these blocks is a minute. And so the first part here, you can see a lot of it goes in sample preparation. That means you get the DNA out of that sample in a rather pure form. You don't have any poisons to poison the reaction, so to speak. Then you have this RT, and by now you know what that is. That's a minute and a half in this case, and it's where I go from the virus, which is an RNA virus, a retrovirus, from RNA to DNA. And then this is where you do this heating, cooling, heating, cooling, heating, cooling, right? And so, as an engineer, we're looking at that, and where can I win? Where can I beat where they are? Now, some of you might raise a hand and say, but Dr. Madou, you don't know the literature. Because way, way back, even in 2015, there were people that were able to do called extreme PCR. And look what they did. 30 cycles, meaning heat, cool, 30 times. They could do that in 1 minute. The reason that they could do it is they use a very small amount of sample. If you use a nanoliter, you can imagine the heat capacity is so small, it's not very difficult to heat cycle it many times. But analytically, it doesn't mean anything. Because if I take 1 nanoliter of a sample from my nose, the possibility that I miss the COVID is very big. So this is in a way where you could see the difference between science and engineering and technology. As a scientist, all these people that publish this had a lot of references. You know, this was like a research stunt. But in terms of practicality, nothing, right? But so I'm just putting that there so you know, I know the literature. As I said, I would be a little bit repetitive because I want everyone to understand exactly where I'm going. I hate to lose my audience. Even if I switch from biology to electrical to mechanical engineering, you need to be on board. Otherwise, it's very tough. Just standing there and just not having an audience that doesn't know what you're talking about, right? So this one you already know. So sample to answer as a first important feature. This you already know, but repetition is good, right? 10 minutes or less, and that's because you know, you want to do it while the patient is in the doctor's office. Now, what is included in that 10 minutes? So here we go to the place where the sample is taken. We do not include in the 10 minutes, you know, the act of taking the sample out. We also don't include storage because we're not going to store it. We're going to go immediately to the result. And so we do include 3, that's virus extraction and deactivation. We do include 4, and by now you all guys know that, right? Reverse transcriptase. We'll do that actually in a minute and a half. You remember that short block in the line? And then qPCR, for people that know a bit about it, traditionally it's been done by cycling your sample between 3 temperatures, 98, 60, and 72. But to gain speed, many people just now cycle between 2 temperatures instead of 3. But it turns out there's some very recent Chinese work that actually claim that by going to 3 temperatures, but making these extremes larger, you can actually be faster. We are analyzing that, reading that, trying to understand is this true or not. This might be a clue for some of you to check up on that. So, but we will use 2 zones, not 3 zones. And then, as you all know, we are after a fluorescent signal that pokes out above a threshold, which means above here you're positive, below you're negative. and that will be called CT. It's the number of cycles. And so you can imagine if you have a lot of COVID and the CT, the cycle number will be low because the fluorescence will show very quickly. So if you're very, very sick and you hear the doctors say you have a CT of 15, oh boy. If you have a CT of 30, 35, you're kind of maybe borderline. So that connects directly to your limit of detection. Let's go to the next slide. So now, to make sure, because suppose I cannot finish my talk in time, I decided to jump on how we solve the problem. And then I hope you will still be interested in me telling the engineering behind it. So, do you remember the time chart? If I can go back a few slides, when I showed that bar, no. Go. Go. This one. You remember this bar, right? So what I have done is I found a technique to bring 1, 2, 3, 4, 5, 6.5 minutes down to 15 seconds. So go now back to the, yeah. So we see, for short, that first segment is the RT, is that reverse transcriptase. I haven't changed that, that's still 1.5 minutes. But you can see that the yellow area there, this has now become 15 seconds. How have we solved it? It's by doing something very, very non-intuitively. You all know autoclaving, right? You heat something in a liquid. Think about your pressure cooker at home, right? Why can you cook so fast and so good? It's because you go above 100 degrees C. And why you go above 100 degrees C is because of the pressure building up in the pressure cooker. Now people say, I can do that. Your RNA is not very stable, it will all disappear. Now what we found is that if you only do it for 15 seconds, you can actually do the best possible sample preparation. So if you do it 5 seconds, not enough. 10 seconds, not 15 seconds. Because then when you go longer, it starts decaying. For people from the materials area, more traditional materials, compare this to rapid thermal annealing. You know what is rapid thermal annealing? It's kind of the same, right? You heat spike it. And you could say this is heat spiking. So the key in reaching this less than 10 minutes is fast and effective sample preparation, removing inhibitors without doing a traditional extraction. So think about engineering challenge now. This is your traditional autoclave. Yeah, you all work with autoclaves, right? Or a pressure cooker at home. So is that possible to miniaturize that and make it disposable? That was the key. And so the materials choice is there because, you know, it needs to be very inexpensive. It's going to be thrown away. But we think we succeeded. So that is our little pressure cooker. And that pressure cooker goes in the middle of a compact disc, a CD. The compact disc will help you distribute the fluid to the places you want it to go. You know, when you spin, liquid will go from the center to different chambers. So in this case, liquid will go from being prepared in the hyperbaric pressure cooker to an inlet chamber, which is below this. And then, and by the way, for the fluidic engineers, this is a real challenge. I need to fill these chambers, and I need to fill them such that there's no air bubbles, and here I have the right reagents, because each of those are different pathogens. So a liquid cannot go in here and then go to this one, or this one, or this one. Please, this evening, sit down and do some fluidic thinking and come up with solutions. This will not work very well if you do it with this way. Does anyone know why? What would be the problem if I have rectangular shapes? See, bubbles hate sharp corners. They also hate flat structures. Because if you have a flat structure, and the fluid moves faster on this side than on that side, what will you have? You will have a bubble, right? And so you really have to think through how to avoid bubbles. Then we also came up with the following. So once all of those are filled, you then will heat. But if you heat, this starts evaporating, and it will mess up everything. So in situ, in the instrument, we heat seal this. All of those, right? And so these were the innovations, the engineering tricks we had to implement to get to this solution. Let me see if I told you everything. So these are more traditional ways of doing the same. If you do heat and dilution, I cannot go into all of the details, but you can see that's 2 to 10 minutes. If you use nucleic acid purification, complex, slower but very efficient, 7 to 45 minutes. And so here with the hyperbaric, we came to 15 seconds. And so this in a way, remarkable progress. I still think that we need to improve this part a lot. I think our heating scheme is clever and new, but the filling of these chambers is maybe not up to snuff yet. So where did I, oh, here it is. If I can have the next slide. So now we're going to start thinking what's behind all of this, how do we get there? Are you guys still with me? Are you following? Or are we good?
Yes, sir.
Yeah, okay. So you remember after T time, which is not a mathematical reason for it to be less than 10 minutes, it's just something you impose, we come to this magic LOD, limit of detection, and this Mr. Lambda, right? So, as I already told you, in the case of gold, with very best equipment affords an LOD of 100 copies per milliliter. And such a low LOD imposes a large sample volume. So I constructed this figure. On this side, it shows the log of the concentration in moles per liter. And in this case, on this side, copies per milliliter. You remember we were saying 500 would be very good. What does that mean for the sample you need? So here at the bottom, you can see that's a picoliter. That's 10 to the minus 18 liters. That's a microliter. You can see if I go down a copy number, the volume becomes bigger and bigger. So if I want to have a very good LOD, I need a big sample, right? And so that's expressed basically in this simple equation, where the volume you need depends on, you all know who that is, Avogadro's number, the concentration, n is the number of chambers I have. Remember the multiplexing. For now, make this 1, and then this is another amplification beyond PCR. I'm also going to make that 1. So let's make it very simple. So then I only have MCI, and you already knows how that went. Now, so M is the number of copies of target, Avogadro's number. Eta is the sensor efficiency, it's the number of photons detected per DNA copy with a value between 0 and 1, and I made it 1 for our thinking here. And we also assume at this moment n is 1. So why did I show now these different lines? So for that we'll go to the next slide. And you can see if I multiplex, so instead of 1 chamber with a number of RNA or DNA copies, I split it. Because, right, I want to look at 8 different pathogens. So let's say I split it in 8 chambers, then in that case, N would be 8, right? And the volume of these separate chambers would be VB. So now I have N not 1, so I have an M over N, and M over N is lambda. That is the number of copies per chamber. And I'm going to go for 8 chambers. So equation 2, equation 3 is the definition of lambda. And you can see it depends on the sample concentration, CI, and the number of partitions, right? Lambda depends on both. So now let's try to hand-wavingly again give you an intuition. What am I really talking about? Well, suppose lambda is very small. How can I make lambda very small? I could make lambda very small by making many, many partitions. I have thousands of partitions, right? And I only have a few molecules, DNA. A lot of them will not get any DNA. So the probability of a 0 at lambda 0,1 is very high, right? Because I don't have a lot of zeros. Now, I can either increase m, right? Or increase n, decrease n, sorry. So now I go to lambda 0.3, and you can see, instead of a Poisson distribution, this becomes more and more of a Gaussian distribution. What that means is the molecules you started with are enough to have 3 here, 4 there, 3 there, 4 there, 3 there. That's kind of borderline, you know, because your CV, your coefficient of variation will still be large. But if I go to a lambda 5, do you see how nicely this is becoming like a Gaussian? Right. So if I say my machine only need to do a yes or a no, you might be okay with lambda being 3 over here. You know, your CV, coefficient of variation, will not be so good because you will miss some. But many times that's good enough. Definitely if you only want yes, no, you're going to go to 5 or even 10 if you really want a very, very good, analytically justified result. This is a rather tough part of the talk, and a much tougher one is coming. So, are you with me on this one? So you understand the connection between lambda and the concentration and this partitioning. Huh? So, if one is interested in a yes-no only, the number of molecules per partition n necessary for detection, you can deduce this way, right? Remember, can I go back for a moment where I showed these different curves? So you can see, I put these different lambdas on here, right? And lambda 1000 would be perfect, right? I mean, it will be easy to detect because there's so much DNA there. This area below lambda is 1. What does that mean? There's less than 1 molecule per sample. By the way, this is where digital PCR works. So don't discount this. This is a very important opportunity as well to do digital PCR, where you can actually quantitate the amount of original DNA that was present by applying the Poisson equation to the distribution of empties and filled chambers. But so, with lambda 3, you're about here, right? And that's the one we are looking at. Let's go back to the slide I was at. Yeah, so I said, let's assume lambda equal to 3. Then I say I need about 500 copies. So where am I ending up? With this volume. That is where that 15 or 20 microliters come from. So I hope you understand now that 15 or 20 microliters is not grabbed out of air. If you want that LOD, that limit of detection, you will need a volume of at least 15 to 20 microliters. So now you have to think, how can I heat cycle 30 or 40 times that volume? And now comes the mechanical, electrical engineers, thermal engineers, how do you do that? And in the beginning when I saw that, I didn't believe that. I said, come on, you have this little bit of liquid, it should be so easy to heat cool, right? And so a lot of materials scientists here just look at how difficult it is. Shall we go to the next slide, please? Well, maybe before I go to the next slide, for the students in the audience, please make a drawing of this, and you tell me by tomorrow how, if I take a volume there of 20 times 8, let's say I take 200 microliters, so I have some extra, and each of those I fill with 20 microliters, right? No bubbles. And make the shape that's most amenable to do it in a smooth fashion. no bubbles, right, in the formation. Now, I want you guys to see if you're thinking through where these numbers are coming from. This 200 microliter is my input. Now I'm writing 100 copies. So why do I say 100 copies will be in my 200 microliters? Well, that is because I'm assuming, where do we go? 500 copies per milliliter. If I have 500 copies per milliliter, how many will I have in 200 microliters? Tell me. How many will I have? 100, right? So, 100. Now, this 100 copies coming from there will go over these 8 chambers. So, if I have a normal distribution, it will be 12, 12, 12, 12, 12, right? Nice Gaussian curve. And lambda, m over n is beautiful, 12, larger than 3. No problem whatsoever. But suppose, should I stop? Okay, I'll finish up. So, I need 100 copies per milliliter. If I want 100 copies per milliliter, my lambda, m over n, will actually be smaller than 3. I can do it. Or I need a much bigger volume. So that is the important thing to know. So now I have the challenge from Shiv to summarize the part for the thermal engineers in a very short amount of time. So I will try to do that. So please go to the next slide. I will skip this. This proves that my prediction is right, and we can do influenza at a lambda between 5 and 3 with 100% to 93% sensitivity. Let's go to the next one. Then you look at all of the competition, and you see that, you remember my 0.4? Okay, that's the one to look. Wow, you really make me jump. That's a difficult one. So, I have that little pocket of liquid. Yeah, you can go to that slide, because that's what the engineers should love. So, I have the PCR solution there in the middle. I have reactor walls, and I have the heaters. I will not go much beyond that drawing and try to just intuitively explain what we are looking for. That the reactor wall needs to be transparent because I'm going to measure fluorescence. And it will contain, hopefully, 15 to 20 microliters, maybe more. And then I have a heater squeezing from the left and the right and making that solution go from 65 to 96 as fast as possible, right? That's that heat efficiency number. And you will see, let's go to the next slide. You need to model this. So guys, take your pen and figure out what is the optimum material for the polymer, the optimal materials for the heater, and most of all, the contact. The contact between the heater and the polymer is the hardest to really know. That's the thermal contact resistance. It's very difficult to understand or know. We ended up having to specify and make polymer composites that had the right heat diffusion coefficient, because you can imagine what would you want from that polymer. It needs to be transparent. The heat capacity needs to be small because, you know, if it has big heat capacity, it will take a long time to heat it up. And the heat diffusivity should be very fast, right? And so keep on going. And I'm gonna, yes. So we did a COMSOL finite element analysis, and I will only show 2 more slides, Shiv, is that okay? So what I'm looking at here is the following. So I'm going from 60 to 96 degrees C. This is the thickness of the insulator, 25 micron, 25 micron. And you can see at point 0, when the heat stamp is applied, that material heats up, the liquid heats up, right? So I go from 95 and I go up, 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 up and up. And you will say that you reached equilibrium when the heat distribution is uniform within 2 degrees C. So you count how long does that take? 1 fringe, 2, 3, 4, 5, 6, 7, about 8. And then you count here, that's about, let's say about 0.7 seconds. You multiply that by 30, right? Because I'm going to do that 30 times. And then you start knowing what the plastic should be, what the thickness of the liquid should be. That's the thickness of the liquid, right? Let's go to the next slide. This shows what happens if the thickness of the insulator is under 50 micrometers. You see this is much thicker now. So do you see how much longer it takes to come to equilibrium, right? Many more fringes, right? So it takes a lot longer. A solution for this problem that some of you might really appreciate, it came from a British company, Express Thermal Cycler. You know what they did? They basically took the heating aluminum foil and put the polymer directly on it. And now you can make the polymer 5 microns. So you can imagine the heating foil and the communication of the heat to the reactor is really by far the best. So let me take over now because I don't want to upset. Oh, why did you went back to the, I want to go to the end. To the end. Oh, you switched the computer already. You're fast. I didn't see you do that. Yeah, if you could put the last slide. I'm sorry, Shiv.
It's such an interesting talk. You don't want to quit. You know.
Good. I mean, I can start taking some questions. I mean,
You can do one thing. Rather than having the instrument so sensitive, if you do the same test a couple of times, say 3-4 times, then the probability of getting...
yeah, that will always improve, right?
Yeah.
Because then, see, but then it takes more time, right? So then we might...
No.
No, I understand that you sample more and more time.
More, but you are using simultaneously, parallelly you are processing.
But yes, see, then you improve the multiplexing, right? And then you need more volume to feed that multiplexing.
That is true.
Yes. Yeah, go all the way to the end. Go. Huh. It's not in here. Oh, after this one. Conclusion. So, RT-qPCR in less than 10 minutes is possible. The emphasis on fast and effective sample preparation, and the company has demonstrated 15 seconds. Maintaining a low limit of detection while moving to point of care is essential, and we've proven 250 copies per milliliter at a lambda of 5. And then spatial and color multiplexing, that is still the real challenge. Look, we want to do 32, and I think we are rather at 5. If the business director would talk, he would say 32. That's the difference between a dean of an engineering school and, oops, I'm sorry, and the marketing director, because they both have a similar function, right? I need funding. And when you get old, funding is good, but you know, also want to figure out how it works. Can you do the next slide? I thought there was another one I put in with some photos. No. That's okay. Thank you.
So Marc, just a point of curiosity. Professor Marc, hello.
Sorry.
First of all, I would like to thank you for introducing a very, very innovative, fantastic piece of research work that you have shown.
Thank you.
It will take a lot of time for the entire thing to really sink in, because you have covered a huge gamut of information. Just for the point of curiosity, you talked about various parameters like lambda, etc. The one that you talked about was that time by volume ratio of having less than 0.4.
Right.
In your research, what is the minimum thing that you have achieved?
With the lambda?
Not lambda, I'm talking about
Gamma,
time by volume.
gamma,
That's
yeah.
it, 0.4.
I think we're close to 0.2. Some people are better, they use 0.1. And it has actually to do with how hard you squeeze that back with your heaters. But there's all kind of problems associated with that, because if you have a closed back, what is the fluidics if the fluid cannot move? And to improve the efficiency, actually, you would like some convection. So it's very contradictory. But if you have convection, it means you need an air bubble, because then, so
you can actually avoid convection just by heating it on the molecular level using just like microwave things. Each molecule gets energized rather than combined.
Yeah, there's people that tried. You're talking basically about cooking a chicken, right? Right? I have a couple knuckles cold, but I know what you mean. For some reason, that also didn't work, but I forget what it is. It might destroy the DNA, perhaps. I need to look at that. Some people have done. Inductively, they've tried, put metal bars in it to improve the efficiency of the coupling. You name it. This is such an important field. Everyone is trying everything under the sun.
I have one question. Actually, thank you very much for your extensive talk. So, end of the day, you have to detect it. You are using fluorescence. So, why not electrochemical detection technique? They are much more erroneous.
You're absolutely right, and that is what I'm currently doing in Mexico. If you want to bring it to this extreme point of care I was talking about, so many problems go. I don't have to be so worried anymore about the quality of that reactor wall. It can even be non-transparent, right? It doesn't matter. Multiplexing becomes a much bigger problem then.
Yeah, actually combining the microfluidics with electrochemical methods are much more standardized, actually, for other detection techniques.
Right. Yeah, I mean, the companies to look at in this area is, for example, Q Health is doing an excellent job along this line. Their COVID test, Q Health, has done on the stock market fantastically. And they have the right solution, but their disposable costs $40 to $50. So.
Thank you.
Okay, I think we will stop here. Mark is going to be still here, so if you have still more questions, discussion, you can talk to him about this interesting topic. So thanks again, Mark, for the talk.
Yeah. Thank you, Professor Shiv Gopal Kapoor sir, and I request Director sir to give a token of thanks to Professor Shiv Gopal Kapoor for chairing this session. Thank you, all of you, for joining us in the auditorium. Now we are going to proceed for lunch at NIFFT Nivas. So all of you are requested to have your lunch and come back at 2:30 for the next session. Thank you.
I request you to come back. Maybe you may need to sacrifice a bit the final. Please be with us. Okay, that's right. Don't worry. India is first batting.
लाइव कमेंट्री फ्रॉम यू टॉस हार गया चलो पहले बंदी बात टॉस हारा है क्या वैसे हम टॉस हार के बैठ चल 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 लंच कर मतलब हो जाए हां हो गया चल लंच Right.